Hey everybody, welcome back to Algebra 1. It is Mr. Marker with you once again. Hope you guys are having a great Thursday so far. Today we are walking through 5.3.3, the last section of Chapter 5 that we're going to cover. Last day of new material, end of the quarter is tomorrow, so if you're missing stuff, get that turned in. Otherwise, it's going to reflect on our quarter grade. Yesterday, we had another quiz. Please make sure you get that taken care of. For quiz number 9, I want to say it is, or 8 or 9, somewhere in that neighborhood. And then homework collection number 9 is going to be open today as well. So make sure you get that taken care of. Get your missing work turned in if you are missing anything. And then today, finishing up Chapter 5. So a lot of good stuff happening. Test is next week, so make sure we're preparing for that as well. If you got any questions as you're studying, make sure you reach out to your grading teacher and ask. So first things first, I'm going to flash up the answers for the homework from last night really quickly. Otherwise, we're going to jump on into 5.3.3. So here we go. There's those answers. Pause them if you need to see it longer, or we're going to keep moving. Awesome. So a little warm up for us. So when we're thinking about a geometric sequence, we should have this on our toolkit from the other day. But what is missing from this formula? So right now we got T of n is equal to blank times R times n. So R is that rate, that multiplier that we're multiplying our initials or whatever we're multiplying in our sequence by. N is the number, is that term number. So we got to figure out what we're missing, and what we're missing I think is going to be that first term, or like our 0th term. So our initial value, that 0 term is what we're missing right here. We have it on our toolkit as G0, or G sub 0, which is again that starting value for our sequence, that 0th term, or think of it as T of 0 when n is equal to 0. So that's what we're looking for. That's what we need to fill that in, that Gorn formula that we talked about on Tuesday. Awesome. So moving on. 5.3.3, is it a function? We're going to compare sequences to functions today. Throughout this chapter, we've been learning about sequences, both arithmetic and geometric. In Chapter 1, we started to learn about functions, but what is the difference? Today, we will compare and contrast sequences with functions. By the end of today, we should be able to answer this question. Is a sequence different from a function? What's the main difference between a sequence, T of n, and the function f of x with the same equation? So that's what we should be working towards today. Starting with 5.1.11, we're going to consider the sequence T of n that we have at the top. So we're -5, -1, 3, 7. We want to create multiple representations of this, i.e. a table, a graph, and an equation. So we're going to write the explicit equation for this one in just a second, and then we are going to also fill in the table. So first, we'll fill in the table. We have term 1, 2, 3, 4, 5, and so on and so forth. Here, we're going to say that this is term 1, this is term 2, 3, and 4. It looks like our pattern here, looks like we're adding the same thing between every term because we have to add 4 to go from one to the next. Add 4. So I'm going to say that we've got an arithmetic sequence here, and our difference is going to be 4. So if we fill in our table here, we can see that same thing again, where our first term is -5, -1, 3, 7, and if we follow our pattern, our fifth term would be 11. So on Tuesday and all of last week when we were talking about arithmetic sequences, our general form for our arithmetic sequence is T of n is equal to our difference times our term number plus our initial value of a0, or a sub 0. So here we have to go backwards 1. So we got to take 4 away for our starting value. And we know our difference is 4, like we talked about at the top. So our equation for this would be T of n is equal to 4 times n and then -9. So here's our equation. We got our table. Last thing we want to do is plot these points on our graph. The first one we're starting with is 1, -5. So we're at 1. We go down 1, 2, 3, 4, 5. Should put us right about there. Then we can add 4 every single term. So 2, -1. 3, 3, 4, 7 is going to be, I think, the last one that we can fit on our graph. Perfect. And that is what our graph of our sequence would look like. So next part, part B, is it possible for T of n to equal 400? Let's figure it out. So again, remember T of n is basically the same thing as f of x. So we're going to say with our equation here, we're going to put 400 in for t of n and then solve for our term number that would get us 400 as an outcome. So 400 is equal to 4 times n minus 9, and now we just got to solve for n. So our first step, we're going to add 9, we're going to add 9, so we get 409 is equal to 4n. Next, we got to divide by 4, so if we move this up a little bit, we should get 102.25 equal to our n value. So is it possible for our sequence t of n to have a number like this, or a term number that is not a whole number? We talked about this a few weeks ago, but we absolutely cannot have a term number that is not a whole number. So this is not possible. Because, like we talked about in the past, n has to be a whole number. N has to be a whole number. Perfect. So let's keep moving. We're going to go to C as we continue down our page. We want to create the same representations as we did for part A, but this time we're going to use function notation. So instead of our sequence t of n is equal to 4n minus 9, now we're using f of x is equal to 4x minus 9. And remember, we talked way back at the beginning of the year how f of x means the same thing as y. So like f of x is equal to y, which tells us that this is an equation for a line. So y equals mx plus b, slope of 4, intercept of negative 9. Hopefully that is very familiar to us. So if we fill in our table and we use our values, this time I'm going to start our table with 0 because we have our starting value. Our y-intercept here is negative 9. Now we're going to go 1, 2, 3, 4, and so on and so forth. Again, we're adding 4 every time we add an x in. So our numbers are going to be the same, negative 5, negative 1, 3, and 7. So far, so good. And now let's plot our line, again, because this is basically, like we said here, same thing as y equals 4x minus 9. So we have an equation of a line here. Let's plug it in, plot our points, and see what we get. So there's our y-intercept, negative 9. Then we can go over negative 1 or 1, negative 5. We got 2, negative 1, 3, 3. Perfect. And that is the last one that is going to fit on our graph. Awesome. And again, because it's a function of a line or equation of a line, we know that it's going to go infinitely in both directions, so we can connect the dots in this case. So let's do just that. If we draw our line in, again, where we know that this is going infinitely in both directions. So thinking back to that same problem that we had before, just at the top, or just a couple of sections above, when we had t of n not being able to equal 400, is it possible for f of x to equal 400? Again, if we solve it exactly the same way, we would still be able to, or we'd get the exact same answer. We're just changing the letters here, so it would be like 400 equals 4x minus 9. We've solved it the exact same way we did before, where x is equal to 102.25. But is that possible for f of x? And if we think back to a couple weeks ago when we first talked about this topic, yes, this is absolutely possible because functions are continuous. Functions are continuous. That means we can plug in any number we want for x, provided that it doesn't make our function undefined. But in this case, we can plug in literally any number that we want for x, and because it's a line, again, it goes infinitely in both directions. It covers all of those values in between our red dots here, unlike our sequence, which is only our restricted discrete outcomes that we see as our points at the graph at the very top part of the page. So again, yes, this is possible, again, because our functions are continuous. Moving on, let's turn the page here. We're going to look at a couple new ones here. So we've got T of n is equal to 2 times 3 to the n, and then we have f of x is equal to f of x is equal to 2 times 3 to the x. So first thing we want to figure out is f of x equals 2 times 3 to the x a function, why or why not, and is t of n equal to 2 times 3 to the n also a function? Let's figure it out. See if those two equations are actually functions. We're going to go over to Desmos and take a look at what the graphs of these two equations look like. So let's click on the right thing here. Here we go. Here's Desmos. So we've got the top equation, f of x is equal to 2 times 3 to the x. So again, as we look at the graph of that equation, it's that red line right here. So as we can see, it goes infinitely in both directions. How we know it's a function is if we think back to chapter 1, we can do something called the vertical line test, which ensures that a function only has one output for every input of x, which in this case, if we take our cursor and kind of scroll back and forth a little bit, we can see as we go left and right that we only have one output per input. And again, this function passes the vertical line test, so it is in fact a function. T of n for our sequence is going to be the exact same thing. So except for the fact that it's only going to have outputs on the whole numbers as we go to the right. So again, it follows the exact same shape, which means that both of those things are functions. So if we go back to our notes here, we can write that down just as we just talked about. Yes, they are functions. Because each input, or sorry about that, each input has only one output. And as a bonus, the graph passes the vertical line test. Awesome. Next, is it possible for t of n to equal 1400? Is it possible for n to equal 1400? Again, now we're trying to do the exact same thing we did before. So let's take a look and see what we get. So again, t of n equals 2 times 3 to the n. And we want to figure out if n is a whole number to equal 400. So again, when we've got, in this case, 1400 equals 2 times 3 to the n. This is going to be a little tricky. So I don't know if we can actually solve this yet. We might not be able to until we get to Algebra 2 in a couple years. So instead, let's do a little guessing and checking here. So let's, instead of trying to solve this, let's plug in a couple of values for n that are going to get us in the ballpark. So if we evaluate, let's say like t of 5, and let's do like t of 6. So if we evaluate both of those, t of 5 would get us 486. T of 6 is going to get us 1458 or 1458. And if we put those on a number line, kind of like this, again, where we've got, this will be 486. Which is t of 5. We've got our other end over here. This is going to be t of 6, where our sequence is 1458. And 1400 is going to be probably somewhere about here, somewhere in the middle. So again, if it's between those two, knowing that we have a discrete function, we cannot have a value of n for that sequence that would make that possible. So it'd be like t of something like, let's say like 5.7. Which is not possible because n has to be a whole number. So this does not work. No, it's not possible. But if we change that to a function notation instead of t of n, where this makes that graph continuous, if we copy this exact setup down below, but instead of using t, we use f, make it a function, not a sequence, f of x is continuous. So if we again copy this exact same thing, we would be able to find a value for x that would equal 1400. And again, this is possible because functions are continuous. F of x is continuous. Let me get my head out of the way so we can finish writing that. Is continuous. Awesome. X can be any number at all because again, f of x, this guy right there, is continuous. Awesome. So let's kind of tie this whole thing together. How are functions similar? How are they different? Again, with functions similar to sequences, what that really is asking, again, really what it's saying is it's the same equation, but t of n is discrete. And f of x is continuous. Where again, we can only use whole numbers, only integers or whole numbers. And for continuous, we can have all real numbers that are able to be used for inputs. So that's how they're similar, that there's the same equation, but different because, again, t of n sequences are discrete and functions are continuous. And again, same equation, we're just changing the letters, kind of like we talked about before. Awesome. We're going to do one more for the video here today. We're going to do 114 right underneath where we're at here. So let's see what we got going on. So Janine was working on her homework but lost part of it. She knew that one output of P of R is equal to 2, or she knew that one output of the function or the equation P of R is equal to 2 times 5 to the R is 78,000. But she couldn't remember if P of R is a sequence or if it's a regular function. So with our team, we want to help her figure it out. So I'm going to rewrite our equation because it's kind of funky the way it's written right up there right now. So P of R is equal to 2 times 5 to the R. So the first thing that I want to do is I'm just going to make a table and just kind of list some inputs and some outputs for this situation so we can kind of see what's going to happen as we go further and further as we increase R. So I'm going to make a table. We have R. We've got P of R as our output. So let's go like 1 through 6 or 1 through 7. So 1, 2, 3, 4, 5, 6, and 7. Again, we're plugging in our value for R. So for example, P of 1 would be 2 times 5 to the first power, which means that P of 1 is equal to 10. And it's the same process as we go down the line. So we have 10. I'm not going to write down every single step for all of those, but basically what we're doing, our pattern, our multiplier is multiplying the previous term by 5. Our initial term would be 2 here, so we're just taking this previous number multiplying by 5. So let's do that as we go down. 10 times 5 is 50. Then we get 250. P of 4 would be 1250. 6,250 would be after that. Then we get 31,000. Can't even read my own writing. 31,250. And then lastly, 156,250. So again, she knew that one output of this is 78,000. 78,000. So 78,000 is somewhere between 156,250 and 31,250. So if that is an actual output of that function, then I don't think that's going to be a sequence. Because again, if we think about our number line like we had before, if I draw that up here again, we've got 156,250, and then we have 31,250. Again, somewhere in the middle here is our output that Janine remembered of 78,000. This is P of 6. This is P of 7. So again, because we're somewhere in between, P would be something like 6.5. Again, P of R would be somewhere like 6.5, or R would be something like 6.5. And we can't have that. if it's a sequence. So if it's a regular function, then we could, so because our output is somewhere in between our two whole number outputs, that means that P of R, oops, let's rewrite that and clean it up just a little bit. P of R is a regular function. Again, not a sequence because the number we'd have to plug in for R to make this true is not a whole number. Awesome. So that's where we're going to stop the video for today. I'm going to put the answers for 115 and 116 in the filled in notes. Actually, scratch that. Only 115. We're going to skip 116 because we're not going to deal with graphing calculators, but try 115 on your own. I'll put the answer in the filled in notes. Last thing I want to leave everybody with is that the homework assignment for tonight is 5.3.3, so please make sure we get a chance to look at that. Remember, homework collection 8 or 9 is going to be due at some point over the weekend, so get that filled in. Test next week, end of the quarters tomorrow. A lot of stuff happening here as we wrap up before spring break. So if you have any questions, reach out to your grading teacher. Otherwise, hope you all have a wonderful weekend, and we'll see you all next week.